The final section of Chapter 7 is 7.8, Improper Integrals. This is an important section both in theory and also in terms of problem solving. So important that I've been taking bits and pieces of this section and introducing all the way from day one, as a matter of fact, or beyond, because I've been writing improper integral problems in Calculus 1 as well, partly as a combination of limit computation and integral problems. I didn't talk too much about theoretical aspect, but that's something we'll have to do now. As far as theory is concerned, it all begins from the fundamental theorem of calculus. Let us use the same notebook that we used in day 1, week 1. And I made a bit of an emphasis here in condition part of this fundamental theorem of calculus. Here we go. Let f be a real continuous function defined in a closed and bounded interval a to b. Then, number 1, the Riemann integral exists in interval a to b. Number 2, antiderivative function exists, capital F prime equals to f. Number 3, the Riemann integral a to b f of x dx can be calculated by capital F of b minus capital F of a, where capital F is antiderivative function. There goes the condition part of the fundamental theorem of calculus. Now, in this section, we are particularly interested in the condition part, not the conclusion part. What if we relax this condition, the blue condition? Instead of considering this in a closed and bounded interval, what if we consider this in an open interval or half-open interval or an unbounded interval? Something to think about. What if my function is not continuous? If it is continuous but bounded, if it is piecewise continuous with just finitely many discontinuity and bounded and so on, then everything is fine, to tell the truth. So we have to consider some singularities, as a matter of fact, like 1 over x function where the denominator becomes 0, or some trigonometric function like tangent or things like those. How do we handle those? Well, let's answer those kind of questions. Let's open up the first section of this notebook and let's classify our improper integrals into type 1 and type 2. Type 1 integrals are based upon relaxing the boundedness condition. Instead of integrating from a to b, integrate it from a to infinity. How do you define that? Integrate function from a to b, but after that, take b to infinity as a limit computation. That's how we can define the improper integral from a to infinity f of x dx. The other one is defined similarly. If you fix arbitrary b, then this integral from a to b f of x dx is valid because this is a continuous function defined in a closed and bounded interval a to b. So this one has a value, and for each values which will depend upon b, we're going to take the limit as b going to infinity. Oh, by the way, if both a and b are going to infinity and negative infinity respectively, we'll have something like this. Both of them will have to go to infinity and negative infinity, but they don't have to be related to each other. In other words, calculate the limit for b first, that must exist, and then calculate a to negative infinity, or vice versa. Calculate the limit a to negative infinity, make sure that exists, and then calculate the limit b to infinity. And these two double limits must share the same value. In short, we are doing this computation and that computation separately only twice. So, in short, everything boils down to either this one or that one. Let's go ahead with an example and let's see. Example A is a non-example, to tell the truth. Negative infinity to infinity v minus v cubed. Well, it's actually too simple to tell the truth. Let's look at the picture here. Does it look like finite area to you? It looks like infinity minus infinity. That's totally invalid. Negative a can go to negative infinity to the left hand side, generating this positive infinity area. And then after that, b has to go to positive infinity, and that just doesn't define anything. If we give some extra condition that b and a are the same, then we may have 0. However, that condition is just an arbitrary condition I just put in, not related to original problem. So you have to say the limit does not exist, or the improper integral does not exist. Let's consider some case that improper integral exists. Computation is rather simple. All you have to do is calculate the antiderivative, and as a matter of fact, you'll have to use substitution technique if you want to get this one right. I'll leave that to you, and the antiderivative turns out to be -1/2 e to the negative x squared. Plug in x equals to negative infinity, x going to negative infinity, you're going to get e to the negative infinity, which is going to 0. And then e to the 0 power is 1, so consequently we have a finite value. Here's a visualization. As a matter of fact, we are looking at only the right hand side part here because integral is going from 0 to infinity. And in the right hand side part, the tail part is decreasing down to 0 so quickly that even though we have unbounded region, the area of the shaded region has to be finite. And clearly we need horizontal asymptote y equals to 0, the x-axis. Otherwise, we cannot possibly have any kind of chance for convergence. Going back, improper integrals of first type, we have to have horizontal asymptote at y equal to 0. In that case, we can define improper integrals kind of like these. Let's go over to improper integrals of second type. What if we have vertical asymptote? Consequently, the function is not defined in the interval a to c. A closed interval a to c. It should be half open, half closed interval, because at x equal to c, the function is undefined. I'm talking too much. I should have showed you the picture. Wait a minute. That doesn't look right. Yeah, here's the picture. Okay, here it is. Graph this function from 0 to 5 I did. But as a matter of fact, the picture does not begin until x equals to 1. So we have this vertical asymptote forming at the boundary edge here at x equals to 1. And then the graph is following the vertical asymptote upward. Now, does the curve converge to the vertical line quickly enough so that the shaded area is finite or not is something we have to consider, and we can do that through integral computation. Calculate the integrand, and we end up with 2 square root of x minus 1. Plug in 5, plug in 1, subtract 1 from the other. What do we have? We have a finite value. That means we have a finite area, and then consequently this integral is valid. This improper integral is valid. So this function, this y equals 1 over square root of x minus 1 function, was valid in the interval. No. Parenthesis 1 comma 5, and then this part was okay, but this part we had open, half open interval. Consequently, we needed some limit computation, which eventually worked out. Here's another situation. Integral from 0 to 4, 1 over x squared plus x minus 6 dx. Let me show you the picture. Here it is. So, at x equal to 0, okay. At x equal to 4, it's okay too. So in closed and bounded interval, this function is defined, but the function was not continuous. At x equals to 2, as you can see in this picture, we had a singularity and we have to work something out. So if we lose the continuity, we have a singularity here, then how do we do that? We decompose this improper integral into two pieces, from 0 to 2 and 2 to 4. Like this. 0 to 2, one integral, one improper integral, and 2 to 4, another improper integral. The first interval is based upon this interval. So domain of this function is actually 0 to 2 union 2 to union 2 to 4. So because of the discontinuity we had, the singularity we had at x equal to 2, which was represented as vertical asymptote, as we see in this graph with all those shading, we were able to decompose the domain into two parts, 0 to 2 and 2 to 4. Neither is closed and bounded interval, so we cannot apply the fundamental theorem. So we have to express them as sum of two improper integrals from 0 to 2 and 2 to 4. 0 to 2, how about this one? This can be calculated through, well, as you see here, decomposition by partial fraction, and we ended up with a couple of logarithmic functions, and consequently we have undefined. The same thing goes for the second. Calculate this antiderivative and do something, and then what do you get? We have two logarithmic functions, and as x approaches to 2, log of 0, that's undefined. So two undefined values. What do you get? We have undefined improper integral. So the answer should be undefined. If you do not see the singularity, and if you calculate kind of like this, let me try to get a incorrect solution here. This is what I'm about to do now is going to be incorrect way, 0 to 4, and then get all the way to 0 to 4, and then we get, well, this is going to be now 0 to 4, and log of x minus 2, it appears, is non-singular. And then if you plug in x equals to 4, what do you get? Log of 4 minus 2, 2, minus plug in 4, log of 7 over 5, and then minus plug in 0, so log of 2, minus plug in 0, log of 3 over 5, and then conclude that this is this integral value after simplification. Let's see, 1/5 log of 3 minus log of 7, isn't it? Well, why am I doing this thing really carefully here? This is incorrect anyway. This is wrong. This is not right. If you simply find out the antiderivative using partial fraction and got that, and apply the fundamental theorem, it looks like it's working, but it should not, because the fundamental theorem of calculus applies for a continuous function defined in closed and bounded interval. Closed and bounded interval, yes, but not continuous, so this whole computation breaks down. So this is wrong, and what we did over here is right.